Welcome to Mrs. Z's Chemistry, the AP version. All right, so let's go ahead and continue our work on titration concepts. Question 13 gives us this new chart where we have 10 milliliters of 0.12 molarity hydrochloric acid, and it's being titrated with 0.02 molarity of calcium hydroxide. We're starting with an acidic pH, which means we have the acid is the analyte, and we're trying to titrate it. Typically, we would not know this molarity here. But in this problem, we're just talking about all the calculations, so it's giving us the molarity of both the acid and the base. All right, so question 13 says, calculate the pH at various points in the titration and enter your answers in the data table provided. Plot the points on the titration curve. Question 14 also says, write a balanced molecular and net ionic equation for the reaction. So here is the molecular equation, and if we recognize that hydrochloric acid is a strong acid, so it completely dissociates, and calcium chloride is a soluble salt, so it also completely dissociates, which means the chlorines then end up canceling. Oh, this is not balanced, by the way. Let's go ahead and balance that first. We just need to add 2's in our coefficients here. So we have H plus and OH turns into H2O. Everything else cancels because everything else is soluble and doesn't change. The water is liquid on the product side, so that's why you can't cancel the H and OH because they turn into a liquid on the product side, which doesn't dissociate, obviously. So let's go back to 13 and start with our pH. Before we have added any of the calcium hydroxide, all we have is a 0.12 molarity hydrochloric acid, and because hydrochloric acid is a strong acid, the concentration of it equals the concentration of H+, which is what we need for pH, because pH is equal to the negative log of the concentration of H+. So the negative log of 0.12, I don't have my calculator with me, but you can do that, and that will be the pH of this one here. All right, so now let's go ahead and add 3 milliliters of calcium hydroxide. And of course, here's our lovely ice table. So originally, we have, again, we're going to be using this equation. Molarity times liters is equal to moles. So for the hydrogen ions, or the hydrochloric acid, we have a molarity of 0.12, and we have a volume of, 10 milliliters, so 0.01 liters. That gets us the moles is equal to 0.0012 moles of H+. So that is the initial amount here. Of hydroxide, we have a concentration, it gave it to us as 0.02. And a volume so far, we have added 3 milliliters here. 0.003. And when we multiply those, we get, let's see here, it still is, well, that would be 0.006. Oops, another 0 in there. But that, if you realize, moles, not molarity, we have to remember, though, that that is for calcium hydroxide. But for every calcium hydroxide, we have 2 hydroxides because of that subscript. So then multiply that by 2, and we have 0.00012. This actually needed another 0 over here. 0.00012 moles of hydroxide. And the reason that is important is because one hydroxide reacts with one hydrogen ion. So if we're adding in double the amount of hydroxide for every mole of calcium hydroxide. So we have 0.00012 moles of hydroxide, therefore that is the limiting reactant. We can only use up that much or react that much. So then when we subtract our initial hydrogen ion and the initial minus the change, we come up with 0.00108. And remember that that is moles. Molarity is moles divided by liters. Moles of H+. Our total now is 13 milliliters, or 0.013, because that is the original 10 from the hydrochloric acid, and then we've only added 3 milliliters of calcium hydroxide so far. And that gives us a molarity of 0.083, and we can round to, let's do 7, or 0.8, there we go. We'll round it to that. Then take the negative log of that, and our pH is then equal to 1.08. Okay, and now we're going to add 25 milliliters. The 3 milliliters was right here on the graph. The 25 is right here. Originally, we still have this amount. When we have 25 milliliters of the base, and remembering that we have to multiply the molarity of calcium hydroxide by 2, or the moles of calcium hydroxide by 2 to get the moles of hydroxide, we end up with this amount of hydroxide, which that means it is still in excess, or sorry, that is still the limiting reactant. So then we end up with 0.0002. And remember that is moles, not molarity. So we got to convert that to molarity by dividing by the total volume, which is now 10 plus 25. So 35 milliliters, or 0.035 liters. And our molarity is now 0.0057143. I know I'm kind of leaving a lot of digits here, but I like being safe, making sure we have the accurate sig figs here at the very end. So then it takes in the negative log of that, and that gets us 2.24. So you can do the ice table for 29.90, see if you can follow that same process here. You can pause the video and work on that. And then when we have 30 milliliters, though, that is right here at the equivalence point. And so we're just going to, because we know this is still a strong acid and a strong base, we know that the pH is a 7, so we're just going to write in 7 because the calculations, again, get a little tricky where the ice tables only look like 0. But then what if we add just probably one more drop of calcium hydroxide, and now we've added 30.1, and the pH is going to increase quite a bit because now we have a whole bunch of calcium hydroxide left over, or hydroxide, the base. So let's go to that. We're going to add in 30.1. So we still originally only had 0.0012, and we have now 0.001204. That is from the 30.1 milliliters and the original molarity that we had from the problem. So now the hydroxide is in excess, and we can only use up the amount of the limiting reactant, the hydrogen. And oops, I did that wrong calculation. So we've got 0.0301. There we go. Okay, so then we have, there's a lot of zeros here. 1, 2, 3, 4, 5. So there's our moles of hydroxide. The total volume of hydroxide is 40.1 milliliters, or 0.0401 liters. The molarity then is, so when we take the negative log of this, that gets us POH, which is 4.00. So then pH is equal to 10. So isn't that interesting? From the equivalence point here, where it was exactly 7, neutral, we add in only 0.1 more milliliters. So not even a full milliliter. And that's probably, like I said, maybe 1 or 2 more drops of calcium hydroxide. And the pH jumps all the way up to 10. And you can solve the next 2 problems similarly with the 31 milliliters or the 36 milliliters. And I've got the ice tables down here for it.